So again, we're talking about ways to determine an entropy change for the second law. And we've said, well, use tables to find S values, little s values. You can use tables for R134 in water or any other substances you have S in your total entropy within your tables. Ideal gases, we don't have that. We have this S degree value. That's something different. The second law itself. So again, if it's adiabatic, this guy goes to 0. If it's reversible, this guy goes to 0. And you see that in the isentropic problems. If they tell you it's adiabatic and they tell you enough information to tell you that it's reversible, we saw this in the last example, then I can use that to figure out, well, delta S is equal to 0. Okay? So the second law itself will allow you to find delta S if you know enough information. These are the common scenarios. There is one more that we will encounter a fair amount. That is heat transfer at a constant or average temperature. If I have heat transfer occurring at a constant or average temperature, then what happens is the integral of this dq over t, if the t is constant, it comes out of the integral. Just like in a calculus class. All calculus rules apply here. Now I've got 1 over t integral dq. And so what we do with that is we say, well, this becomes then q net n divided by t. How do we do that? Well, if I integrate dq, I just get q. And if I integrate dx in a calculus class, I just get x. So if I just integrate dq, I just get q. And again, we said n was positive, out is negative in this case. So if I add heat in, I'm going to increase the entropy, so that's positive. So q net in, the difference between the heat in and the heat out, divided by the temperature at which that occurs, if that temperature occurs at a constant temperature, or if that heat transfer occurs at a constant temperature, and this crazy looking partial integral simplifies simply to q net n over t. Take everywhere that heat transfer occurs, if it's coming in, add it, if it's going out, subtract it, divide it by the absolute temperature at which that heat transfer occurs, and that's all this term becomes. So again, finding delta S, well, if I can go look these up, fine. If not, can I use this to figure these out? Well, if I have heat transfer occurring at a constant temperature, this just becomes q in over t, or minus q out over t. If I know it's reversible, this goes to 0. Those are kind of my two options with SGen. Is can I determine that it's 0, or is the problem asking me for it? If the problem's asking, is this process possible, or is this process impossible? They're asking to figure out SGen. Okay? But if they're giving enough information to determine if SGen is 0, well, then that's easy. It just goes to 0. Then I've got to deal with this. Okay, what do we know about the heat transfer? Is the heat transfer 0? No. Okay, can I use the first law to solve for the heat transfer, and do I know if it occurs at a constant temperature? Okay. A common problem is you can find both S values, you know it's reversible, and they're asking you to, or you have to use the second law to find the heat and plug that heat into the first law to find the work. That's a completely normal, classical thermodynamics problem. Okay. All right, so we'll see those as we move forward, right? And that's the slide here. Okay. The third option for determining delta S is what we call the Gibbs equation. If you've seen this in chemistry, you probably called this the Gibbs free energy equation or something like that. It seems like it's been a hot minute since I've had chemistry, but I think they use it to figure out, is this process possible, or is this chemical reaction possible? Okay. All right, this video is going to be short because I'm going to pull notes out and make sure I can put my hands on it very quickly here. I think this is it, actually. I can put my hands on it quickly. I can probably do the derivation from memory. I've got it. All right, I've got my notes here. Okay, so let's derive the Gibbs equation. Okay. Like I said, I could probably do this from memory, and I should have had my notes ahead of time. I apologize for that. But here we are, ready. So let's talk about Gibbs equation. Gibbs equation. So if we start with the first law, let's write it this way. Let's kind of write it in a traditional way. We'll say that Q net in minus W net out is equal to delta big U. We've seen this form of the first law before. We've talked about it. We said this is the difference between Q in and Q out. This is the difference between work out and work in. Okay. So if we consider a small slice of this system. Okay, now if you're following along in the textbook, I believe they do this derivation. I think I add some steps in that maybe they don't. Okay, so again, we've talked about this Q. We don't know how this heat transfer is occurring, what variables are at play, so we've got to use an inexact differential. We're going to look at a tiny little small differential size slice of this system. And so what's going to happen is we're going to have a differential size amount of heat transfer. And we're going to use an inexact D to refer to that. And we're going to use an inexact D to refer to the work. And that's going to equal D big U. Okay, so a tiny little amount of heat transfer minus a tiny little amount of work out is going to equal a tiny little change in internal energy. Okay. Now, recall that the work is equal to the integral of pressure with respect to volume. Right? For boundary work, the work is equal to the integral of pressure with respect to volume. And so what that means is that if I look at a tiny little slice of this work, a differential amount of this work, that's equal to the derivative of this. Well, the derivative of the integral is just the p dv. Okay? So a differential little amount of work occurs when I've got pressure changing through volume, or pressure applied through a change in volume. Okay? And remember, we just talked about that if you know the integral of temperature with respect to entropy for a reversible process, that gives you amount of heat transfer. And if I take the derivative of both sides of that equation, look at the differential slice of that expression, that means del Q is equal to T ds. So if I plug this in here, and if I plug this in there, this is what I get. I get T ds minus P dV is equal to du, and all the inexacts go away. These are all regular, ordinary differentials. So TdS minus PdV is equal to du. And if I, let's go, we don't know how big our system is or small our system is, so let's divide by mass. And then it doesn't matter how big or small my system is. Well, the temperature is, it doesn't care how big or small the system is, it's still temperature. The entropy, though, that is an extensive property, so it does depend on how large this system is. So that's Td little s minus Pd little v, again, big V divided by mass is little v, and big U divided by mass is little u. Okay, so I can relate a change in entropy to these other properties. Now, again, Steve, what the heck are you doing? Why are we doing this again? Remember, we're trying to figure out delta S. We're trying to figure out a change in entropy. So I'm going to solve for this change in entropy. We're trying to use Gibbs equation to quantify a change in entropy. So I'm going to solve for that change in entropy. Move it over, so let's see, so we'll just move that over and divide by t, so this is equal to, let me look at my notes so I don't go too far off script. Okay, yes, ds then is equal to du over t plus p dv over t. And this is what we call the Gibbs equation, the Gibbs free energy equation. A change in entropy is going to be determined by a change in internal energy per temperature and how pressure, specific volume, and temperature all change. Okay. You'll find forms of this using density instead of specific volume, and that's okay. This form's okay. Also, recall we can write it a slightly different way and say, well, H. Remember, enthalpy is the sum of U and the product of pressure and specific volume. U plus PV is H. So that means that dH, a tiny little change in enthalpy, is going to be equal to the derivative of this side. Derivative of this side is equal to the derivative of that side. So derivative of U is just du. For this other term, I've got a product rule I need to apply, so I've got P times V. So this is going to be P dV plus V dP, or dH minus V dP is equal to du plus P dV. Notice this is du plus P dV. That's the same as dH minus V dP. So a change in entropy I can find based on a change in internal energy. Right? du over T plus P dV over T, or I could also use this side. This and these are interchangeable, so this is also dH over T minus V dP over T. Either of those work. So this Gibbs free energy equation. Again, our goal here is to try to determine changes in entropy. Organized here. Thank you for your patience. So we're using this to determine changes in entropy. So to do that, I'm not going to use this differential equation. Let's see if we can use this. Well, we are going to use this differential equation. Let's see if we can get it to an algebraic expression that we could possibly use. Do you know of any substances off the top of your head where you could determine how U changes as temperature changes, and how P, V, and T are all related to each other? Can you think of any substances where we know that about the substance? How U changes as a function of temperature, and how P, V, and T relate to each other? Can you think of a substance that we know that? Well, I can. For ideal gases, right? For ideal gases, we know that du is equal to C sub V dt, and that dH is equal to C sub P dt. Right? We also know how pressure, volume, and temperature relate to each other. We can assume that they're reasonably linear in terms of how they relate to each other. Well, that's pretty cool, right? So off of this, we can say, well, that means that P over T is equal to R over V, right? Okay, thank you. How are we on time? I got a second or two. And I can also say that V over T is equal to R over P. So I can plug these into these expressions and do some algebra, and we'll pick up there on the next video.